Hello everyone, and welcome to the second part of the tutorial. We are going to pick up from where we left off in the last class. If you remember, we were talking about spreadsheet modeling as one of the tools that's very commonly used in supply chain management. The first category of applications that we've talked about pertain to demand planning. If you recall, we talked about new venture decisions under various types of conditions, under conditions where you have probability information available to you, and in conditions where that information is not available. So we've talked about various metrics that you could use in a demand planning scenario. We also briefly talked about facility location, and I introduced you to a few heuristics that can be used for facility location, and we also talked about the centroid method for facility location. In today's tutorial, I'm going to expand on that definition. I'm going to expand on the facility location problem that we talked about before, and we're going to talk about optimum facility location, and for that we're going to use Excel's solver tool as the tool of choice. In addition to that, we're also going to talk about transportation and transshipment networks, and together both of these scenarios can be categorized as supply network planning scenarios in supply chain management. So a variety of industrial applications and enterprise information systems help us work with these types of problems. ERP systems in particular would have different modules, different functional modules that have this capability and that have the functionality to work with the types of problems that we are using Excel spreadsheets for. But just to show you what the functionality is and how various algorithms work, how various programs work, that's why we're looking at Excel spreadsheets as the tool of choice. Before I go on to talk about today's problems, I just wanted to touch upon the idea of optimization. That is sort of a prerequisite to our discussion for today. We are, in general, going to talk about a couple of different types of optimization problems. And what I mean by an optimization problem is that it simply refers to a scenario, or it simply refers to a particular hypothetical situation in which you have to select the best possible element from some set of alternatives that you've been provided with. At its simplest, you need to formulate a problem in order to minimize or maximize a certain quantity or a certain function. This could be something like cost of production or the profit that a firm makes. And you do that by systematically choosing between values of variables that you have, and you're given an allowable set of values to choose from, or you're given certain sets of constraints to work within. So with optimization, there are specific terms that are very commonly used, and I'm going to introduce you to those terms before we move on to the actual discussion for today. With optimization problems, we talk about the objective function. This is the actual function or quantity which you're trying to maximize or minimize in your solution. So this acts sort of as a scorecard on which you measure how attractive your overall solution is in terms of maximizing your profit or minimizing your cost. The second term here that we're going to use are decision variables. These are the variables that you are trying to change to find the optimal solution overall. So you're trying to come up with optimal values for these decision variables, which will affect your objective function and will change the objective function's value to either increase it or decrease it. So decision variables could be things like the number of units you produce per time period, or it could be the number of units that you're shipping along specific routes if we're talking about a transportation problem. So decision variables are what in Solver you refer to as changing cells. So these are the cells in your spreadsheet that you are going to play around with, and you're going to change the values for these decision variables to see what type of optimum solution or what type of solution you're getting in order to optimize that value. The third term here is that of parameters. Parameters are coefficients or constants in your problem that you cannot change during the implementation or during the formulation of the problem itself. So these are certain things that you've been provided with early on, and you cannot change their value. So this could be something like the cost of production, the unit cost of production, or the cost of distribution along certain routes, and you just have to accept them the way they're provided to you, and you have to formulate them in your problem as such. The fourth term here is constraints, and these are limitations that can restrict the possible choices you have for your decision variables. So you mathematically express these constraints with equalities and inequalities. So greater than or equal to, less than or equal to. There could be upper limits and lower limits to certain things, and you express them as your constraints. So for example, in a transportation problem, there might be a maximum number of units that can be shipped from a particular supply point to different demand points. So that could be a constraint. Or a certain demand point requires a certain number of units to be shipped to it, and that could be a constraint in the problem itself. Once you've taken all of these things into account, you can come up with various types of solutions. And the set of solutions that you can get within the constraints is what is referred to as the feasibility region. So the feasibility region represents all permissible combinations of decision variables, which means that there can be many possible solutions, but using different tools and algorithms, we are interested in finding the best possible solution. And that is why we're using different tools for optimization. Programming is one example of a subset of optimization problems. So this is one category of an optimization problem. It's very commonly used in business and economics, along with certain assumptions. And with these assumptions, we can solve various types of problems. One of the main assumptions in linear programming is that your objective function and your constraints are going to be formulated as linear equations, which simply means that you cannot multiply decision variables together, so you can't take products of decision variables, or you cannot use powers of decision variables, so you can't use x squared or x cubed or any of the powers of decision variables. That is the simplest way to think about what linearity assumption is all about. Also, most of the time in your constraints, you're also going to probably have a non-negativity constraint, which again means that your decision variables can only accept positive values or 0 in certain situations. So all of your decision variables, once the solution is formulated, have to be greater than or equal to 0. So that should explain what optimization and linear programming is all about. Again, the term programming should not be confused with computer programming. It has nothing to do with computer programming. You're just formulating a program, or you're formulating a solution to a specific problem. And linear programming is just a technique which is used for resource allocation problems. So you have a complex resource allocation problem, and you want to allocate your resources among various options that you have. And for that, linear programming is a specific technique. There are various ways to solve linear programming problems. We are going to use Excel's solver add-in as a tool for linear programming problems. It solves various types of optimization problems, including linear programming. It's a tool that's available through your Excel spreadsheet. For those of you who are using Excel 2007, you'll have to go into your ribbon. I can show you very quickly where you need to go. So just to quickly show you here, what you can do is go under your ribbon, Excel options, add-ins, and you should see a list of the various add-ins that are enabled, and you should see solver listed in there. If you don't find this in the list, then you can just click on the go button here, and it will have a list of add-ins for you to choose, and you could choose solver from there. For those of you who are using an earlier version of Excel, this item might be under your tools menu bar at the top, tools menu item at the top, and you can choose solver add-in from there. If you haven't used solver before, You might want to also look up the tutorial that's available online from www.solver.com/tutorial.htm. This actually is the website for the company that develops various tools, including Excel Solver, and they actually have another premium version of Excel Solver as well for companies that are using this for more advanced types of problems. So you can go to that website to check out more. So Excel Solver or linear programming in general is used in supply chain management in various areas for various purposes. These are just a couple of quick examples for where you might see linear programming be used in supply chain management. In our examples today, we're actually using it for a distribution problem or a transportation problem where we're interested in minimizing the total shipping cost or minimizing the cost of transportation between supply points and demand points. That's one category of problems. Another category of problems in supply chain management where linear programming might be helpful are what are known as blending problems. This is where you're interested in allocating or combining different raw materials of different types and grades in order to meet the demand and maximize your profit or minimize your overall cost of production. So blending problems is another example here, especially in organizations where they have access to different raw materials and components and they can mix and combine different grades of those raw materials. Another category would be in scheduling, especially production scheduling. So if you want to allocate your machine time and labor time to various tasks, this is especially relevant in a job shop environment where you want to minimize the total cost of production and minimize your total inventory costs as well. So linear programming provides a good technique to solve those types of problems as well. So there are various applications of linear programming. You can use Solver or another advanced tool for formulating and coming up with the optimum solution for these problems. This company, Frontline Systems, which I've mentioned before, they actually also provide advanced toolkits for developers who want to include this functionality in a program that they're writing or in an application that they're developing for an organization. So we are going to use Excel Solver because that is the most commonly accessible and easily available tool to use for optimization problems, and it will do the job in our scenario. So with that short introduction, let's get started with our transportation problems. That is the category of problems that we're going to talk about today. Transportation problems typically are categorized under network optimization or supply network planning specifically, or these can be referred to as distribution problems as well, because what you're trying to do is come up with the best possible solution to distribute raw materials or components or a finished product from various supply points to demand points, incurring the least possible cost of transportation. First of all, we're going to talk about the notation we're going to use to depict these transportation problems. There are two most commonly used ways of depicting these problems: the transportation grid and a graph diagram. They depict the flows between supply points, which are also known as sources, and demand points, which are also known as sinks. So let's look at a transportation grid first. It's a tabular format representation of demand points and supply points. Along your vertical axis, you have all of your sources or your supply points. In this case, we have three supply points, A, B, and C. On the x-axis or on the horizontal axis, you have your sinks or your demand points. In this case, we have 4 demand points, 1, 2, 3, and 4. So the table between these supply points and demand points are meant to show you the actual flow of material from the supply point to the demand point, as well as the cost of transportation between specific supply points and demand points. At the end of the row, what you see is the supply that is possible, the maximum supply that is possible out of a supply point. So in this case, what we're saying is that point A can supply a maximum of 55 units or 55,000 units if